Welcome to The Explainer. Today, we're exploring the hidden architecture of atoms.
So, how do atoms build everything? Turns out it's not random. They use repeating crystal structures.
To get this, we start with a basic building block, what we call the unit cell. Next, we count an atom's closest neighbors. This is its coordination number. And finally, we measure packing efficiency using the atomic packing factor, or APF. All right, let's dive in with the most basic one, the simple cubic structure. Now, it looks like 8 atoms, right? But they're shared, so each cell really just has one.
In this simple setup, every single atom has exactly 6 immediate neighbors. So, what does this mean? It's only 52% full. That's a ton of wasted space.
Okay, so how can we pack things tighter? Simple. We start adding more atoms to the cube.
First up is body-centered cubic. You see this a lot in metals like iron and chromium.
That one extra atom right in the center, it brings our total up to 2 per cell.
And that central atom now touches all 8 corners, bumping the coordination number up to 8. The result? We've jumped to a much better 68% packing efficiency, a big improvement. All right, next is face-centered cubic, which has a whole different strategy for getting dense. Instead of one in the middle, we add atoms to each face. That gives us 4 per cell. And check this out. This super dense layout gives each atom a whopping 12 neighbors. So what's the payoff? Our packing factor skyrockets to a seriously impressive 74%. But wait, there's another way to hit that maximum density: the hexagonal structure. You find this in metals like zinc. Its unique hexagonal shape packs in 6 full atoms. And just like face-centered cubic, it's also got that super high coordination number of 12. And get this, it has the exact same packing efficiency as FCC, a perfect 74%. Okay, let's put it all together. You can really see the clear progression in density here. So the big takeaway? Denser packing often leads to materials that are more malleable and ductile. And why does this matter? Well, this hidden architecture is what dictates a material's real-world properties.